Hello, good evening, everyone. So today we're going to start with the review of first order transients. This should be something that you studied in the last semester in Networks 1, but in preparation to going towards second order transients, I wanna review this topic a little bit. Right? So again, I mean, this topic of study is called transient analysis. Right? So a lot of the techniques that you studied in Networks 1, you would call DC analysis. Right? Most of those techniques have to do with solving circuits. So that was your introduction into a broad topic called circuit theory, which implies modeling electrical phenomena, electrical circuits as lumped elements. So you have resistors, R, that's the first lumped element you learned. You could have resistive networks, R1, R2, R3 connected together. They could be connected in series and in parallel. You have meshes, things connected in series, right? And then the other kind of lumped element you learned is the capacitor. Then you have the inductor. I'm just, drawing an expansive L1, let's say C1 circuit, R11, whatever. And then the circuit has connected to it sources. Those sources could be voltage sources, V1. They could be current sources, I1. Right? You've learned about dependent sources, right? Like I said, dependent source that depends, like for example, a current source that depends on a voltage somewhere, or a current source, a current source that depends on a voltage somewhere, or a current source that depends on another current. You could have a dependent voltage source. Right? So there's a slew of elements, two-port elements that you learned about. And you know how to connect, how to analyze them in circuits. So you have different circuits with those elements connected together, and you study the number of broad techniques of analyzing those circuits, getting solutions. But during all of this, the focus was on circuits. No matter how complicated the circuits got, you were focusing on circuits where the sources feeding into the circuit, the voltage and the current sources, that the independent voltage and current sources were constant. They were not changing with time. Right? So because they were constant, your analysis technique is called DC analysis. Right? And DC analysis in many ways is simpler than AC analysis. It is still a bit involved because you have to do all the techniques that you learned of mesh analysis, nodal analysis, right? Nodal, and then some other techniques that you learned, such as voltage divider, current divider, Thevenin equivalent circuits, Norton equivalent circuits. Right? So there's a lot that you covered in circuits 1 and networks 1, but you did not. All of that was constrained to the domain where the forcing functions, or so-called forcing functions, or the sources of the circuit were constant. They were not time varying. That's one. And second, your circuit itself was static, meaning the circuit did not change with time. There was no switching in the circuit. There was no switch that moved from one place to the other. The circuit topology, so to speak, did not change with time. It remains static. So the circuit remains static, did not change with time, did not evolve with time. The values of R or L or C did not change with time. The gains of the dependent sources did not change with time. The sources themselves did not change with time. When we move on to the domain where things start changing in time, that's when we move to the domain of transient analysis. And transient analysis is a special case of variation in time. It's not the most general case where things vary constantly all the time. It's a special case where you have a transient. What does a transient mean? Transient mean a sudden change. So you have a sudden change in the conditions of the circuit. Some voltage suddenly changes. Some switch suddenly throws. Some resistor suddenly changes from one value to the other, right? And then after that sudden change, so everything is stable, static, and then you have a sudden change, and then things remain static. So what will happen is that during after the sudden change, you will have a transient region where things will be moving around until things reach steady state again. Right? So this is the domain of this area here is the domain of transient analysis. And transient analysis is for linear circuits, which is what we are studying in this course. Those transients are analyzed using the mathematics of differential equations. And for first order transients, we're going to study first order ordinary differential equations. This is the mathematical language that is used to study those kind of transients. And after that, we will move to second order, in which we will solve those systems using, or circuits using, second order ODEs. ODEs, are a very general topic. Typically, ODEs, ordinary differential equation, which contrast, of course, with partial differential equations. Partial differential equations are equations where the variables that we're solving for are distributed over space and time. For example, if you have a room and you have the temperature in space and time, the temperature spread across the room. The equation that you would write for such a thing is called a partial differential equation. If you consider the temperature to be uniform, the temperature is everywhere the same in space, so you end up with solving just T with respect to time. You don't have a spatial distribution of temperature, then the equation you will get will be most likely an ordinary differential equation. That the rate of change of the variable you're solving for only changes with respect to time. It does not change with respect to space, any direction of space, so on and so forth. Right? So that's the difference between partial differential equations and ordinary differential equations. Ordinary differential equations could be subdivided into equations with constant coefficients, and those we can solve easily, we know how to solve, and then those with time varying coefficients. Those are unsolvable. Only very special cases of those kinds of equations with time variable coefficients are solvable. The vast majority of them are unsolvable, and there is no closed form solution to them. We have to do use numerical techniques. Right? While ODEs with constant coefficients are easy to solve, and we know it's a solved problem. We know exactly how to solve them. Right? So we said transient analysis is concerned with analyzing what happens if there is a change in the network. Either the voltage changes suddenly, right, and then or the network itself changes suddenly due to the throwing of a switch, right? So it's a special kind of change. It's not a change that's occurring all the time. It's not, if we have a change that's occurring all the time, we end up with a time varying ODE. No, that's not what I mean by transient analysis. I mean, it's like kind of like I said, it's a change that happens suddenly, and then things get steady after a while. Right? It's a sudden change in the network. And the dynamics of first order. So we're going to start with first order transients. The dynamics of first order transients are governed in your circuit. To have them at all, you need to have in your circuit energy storage elements. Or else if you have like a step change in the condition of your circuit, either the network or the voltage, if you don't have any of those energy storage elements, nothing will happen. You'll just have a step in your solution. Only if you have the energy storage element will you have this transient behavior that you need to study. From the last course, prerequisite of this course, you know that what the energy storage elements are, right? You know they are the inductor and the capacitor, right? The equation, that the voltage current relationship for the inductor is VL, the voltage across the inductor, equals L DIL. This is IL, this is a convention, over dt. And then for the capacitor, this is IC going in. You know that IC equals C. This is the capacitance, inductance, dVc over dt. Right. So only if those elements exist in your circuit do you have a possibility of a transient. And if you have one of those energy storage elements, only one, you get a first order system. If you have two of them, you have a second order system circuit, and you need to study a second order response. If you have three of them, you have a third order system. If you have four of them, you have a fourth order system, so on and so forth. All we need to know to solve systems in general is to solve the first order case and the second order case. We don't need any more than that, because if we solve the first order case and the second order case, we can solve any higher order case. This is very analogous to solutions of polynomials, right? So if we have a first order polynomial like x plus 5 equals 6, we can solve it. If we have second order polynomial, to solve it in general, we need to introduce complex numbers. To solve a higher order polynomial, we don't need to introduce a new number system. Complex numbers are enough to find all the solutions of any higher order polynomial. That's why complex numbers are so crucial, and because polynomials occur when we solve differential equations through the characteristic equation. Okay, so to summarize, the transient conditions we will be studying is that we have a certain circuit. Circuit is in a steady state. It's constant. It's not varying. It's reached a steady state. We could call this the initial steady state. Something changes. The circuit changes. Switch gets thrown. Right? Something happens, and we enter a region, what's called the transient region. The voltages and currents in the circuit are varying. A transient happens, but then things settle down after the transient ends, and we end up with the final steady state. This is the region that we will be studying. What happens within this region is what we will be studying in first order and second order analysis. First order and second order systems or transients. From this quick introduction, what can you say is the most important parameter for the first order transient? Right? One of the most important parameters you can think of is how long does this region last? Right? This period of time where the transient happens until it ends and we reach steady state again. How long does this last? And we quantify this period by a parameter called tau, which is the time constant. The time constant is a way of quantifying how long does this transient in general last. And to get a handle on this transient and to understand the response equation, first order transient, we will of course start with the basics. The basics are through the differential equation. We have to solve the differential equation, but after that we can apply a more methodical step-by-step method. So I'll talk about that also. Okay, so let's give an example. Quick example is, for example, like a practical example, a flash circuit for a camera. How does a flash circuit for a camera work? Well, we have a certain voltage source, battery maybe, and then there's a resistor, RS, and then there's a switch. The switch gets thrown in this direction. We have a capacitor, right? So before the switch, like in this initial steady state, the switch is connected to here, so the capacitor gets charged by the battery, right? And then when it gets charged to a certain voltage, right? And then we have when the time comes, the switch gets thrown to the other direction, and all the energy in the capacitor gets dissipated in the resistance that represents the lamp, let's say, lamp resistance. This charge in the lamp resistance causes the lamp to flash. And if you have a scope or you plot the voltage, let's say after the voltage across the voltage on the cap, let's say we're plotting the voltage on the cap, we'll see something like this with respect to time. Initially, we will be at Vs, which is the battery voltage, and then when the switch gets thrown, the capacitor will quickly discharge. This will generate the flash, and then once let's say the switch goes back towards the battery, the cap will charge up again. So this is the charge time. And those times, this time and this time, this charge time and charge time is going to depend on the network, on the circuit, on the parameters of the circuit, on R1 and R. Right? That's what first order analysis gives us. It allows us to understand how does that time constant change depending on how the network changes. So this is like a practical example. Now let's move to reviewing solving for the first order response. I hope this is not new. This is something that you've already studied. I'm just reviewing it. Right? So typically what will happen is that you will have a certain circuit, and then you will apply any known circuit analysis technique that you've already studied. You could apply KCL, you could apply KVL. Those are the basic techniques for circuit analysis. And then you end up, after you apply those techniques, you end up with a mathematical differential equation, first order differential equation, which you solve to get the transient response. So let's talk about solving the differential equation. Before worrying about how do we get the differential equation from the circuit, let's talk about how do we solve the differential equation. So typically a general first order differential equation will look something like this: dxt over dt plus some constant x of t equals f of t, some input here. So this is called the forcing function. This is like an input that drives the differential equation or drives the system. This could be like a voltage source or current source. But right now it's a general forcing function. Don't think of it as any source. Don't think about x as any voltage or current. It's just a general variable. We want to know how to solve a first order equation in general. And from your study of differential equations, you know that any differential equation in any ODE will have a general solution that's constructed from the composition of two solutions. It will be constructed from what's called the natural response. So this is the solution of the homogeneous equation. This is the solution of the equation dx over dt plus axt equals 0, right? Any solution to this equation is also a solution to this equation, right? Because, I mean, you plug it in, it's equals 0, right? Plus the solution that gives you f of t. So let's say this is the solution that gives f of t. So if you plug this in into the differential equation, if you do the x of pt over dt plus a x of pt, you get ft. Right? So this is called the particular solution, right? And it makes sense that the particular solution plus the homogeneous solution is also a solution, because the homogeneous solution or the natural response, I mean, if you plug it into the differential equation, it just gives you 0, right? It does not. This gives you ft and this gives you 0. Anything that gives you 0 is still going to be a solution for the general equation, right? So, I mean, in short, for any ODE, you always solve the homogeneous equation first, the equation where the force and function is 0. And that solution will always be part of the general solution. Only after you solve the homogeneous equation to get the natural response do you solve for the forced response. Okay. Right. And we know how to. I mean, there are, as the expression says, there are many roads that get you to Rome. So there are many techniques for solving the homogeneous equation. You could do integration, right? I could solve it by integration, right? I could do, it's a very simple separable equation. What does it mean? What do I mean by separable equation? Well, I can arrange it in this way. I can say dx equal dx over dt equals minus a x, right? And then I can do this dx over x equals minus a dt. This is a famous method of, this is the, I'm applying the method of separable, it's a separable equation, right? So I'm using the notation here, but this is a very common thing that people do when they're solving differential equations, right? So I have this form. All I have to do is I have to integrate both sides. What is this integral? This integral is ln x, right? If you differentiate ln x, you get 1 over x plus c plus some constant. What is this? This is minus a is constant, t, right? I can take c to the other side. I end up with minus c. I take the exponential of both sides, e ln x equals e minus at, e minus c. Remember the property of the exponential, ea plus b equals ea eb. I can lump, this is just a constant, c is a constant. So e minus c, I can lump it as just a constant, call this constant k2. Right? What's e to the ln of x? E is the inverse of the logarithm, right? You remember that from calculus. So this is just x. So this is xc of t is going to have this form, x2 e minus at. This is the natural response. Right? So this is one way of finding the natural response. Another way, which is kind of helpful and is going to lead us to the method for solving typical method for solving the second order differential equation, which is the method of finding the characteristic equation. What do I mean by that? I mean that we know that the differential operator dx over dt, I know that if x of t equals e lambda t, right? First, I know that d et over dt equals e of t, right? That's the basic property of the exponential function. If you differentiate it, you get the same function. Right? And then if I have a lambda t, I use the chain rule. So I first differentiate the exponential, and then I differentiate what's inside the exponential, so this becomes lambda. Okay, so using this property, I can assume that the solution is going to be E lambda t, and then I go back, right? I can assume that the solution is going to be E lambda t, and then I just solve for what lambda should be. So this is a very common technique of solving the ODEs by solving the characteristic equation. So I have my the homogeneous equation dxc over dt plus a xc equals 0. I plug in my assumed solution, and the neat thing about the exponential is when I differentiate it, I get lambda e lambda t plus a e lambda t equals 0. I can divide everything by e lambda t, and I end up with lambda plus a equals 0. So that's the beauty of the characteristic equation. I turn the differential equation into an algebraic equation. And this equation tells me that lambda equals minus a. So my general solution should be E minus AT, right? Similar to what we got here. Of course, times a constant, because right, if your general solution, you could have any constant here, right? So the general solution will be a constant. If this is a solution, a constant times the solution is also a solution. So I want to get the most general solution, so I just multiply it by a constant. Okay. So remember this technique of finding the characteristic equation. It seems kind of like silly here because we can directly integrate the differential equation. We don't need it. But for a second order system, we will need to use it because it will make finding the solution of the system easier. Much easier. Integrating a second order system is harder. Okay. Right. The point is we found the natural response. We found the natural response. The homogeneous solution, the solution of the homogeneous equation. Now we want to go back and find a particular solution. So I have dxt dt plus a xt equals f of t. Again, there are many ways of finding such a solution. Well, I mean, I told you, if we have a time varying system, if I have f of t that changes generally with time, it's a variable. It's a there won't be like a. It will be hard to find the solution. We need to use more advanced techniques. We need to use something like the Laplace transform. If a is varying with time, forget about it. The solution will be impossible to find, even with the Laplace technique, right? But we want to limit ourselves to we don't want to go to the most general technique. We will study the Laplace technique at the end of the semester. What we want to go with is cases where we have like a sudden change in the network, but the sources themselves are constant. So f of t does not depend on time, it's just a constant. This is the particular solution that we want to find. Right? And there are many ways to find this, to solve this, but typically what people do when they try to find the particular solution is they again assume a solution for xp. This is xp. Assume a solution for xp that has the same form as the forcing function. The forcing function is a constant, so they assume that xp is some kind of constant, k1. Right? Apply this to the equation. So dk1 by dt is 0 plus a k1 equals a. This tells me that k1 needs to be a over a. Right? I mean, all that matters here is that the particular solution for this case is constant. It's going to be constant. So this allows us to write the general form of the solution for a first order equation. It's going to be always a constant. We don't have to write it as a over a. I'm going to leave that out. right? I'm gonna just write it in the most general form. It's gonna be a constant, always gonna be a constant, because the most general form is useful. We can apply it everywhere at any general problem. And then plus a constant, e minus a of t. Another thing I want to do is, instead, this is just a constant. Instead of a, I want to put its reciprocal, some reciprocal of it. And this reciprocal, I'm going to call it tau, the time constant. It divides time, so it must have units of t. Right? Whatever term here attached to the exponential must be unitless, right? Because it must be unitless, tau must have units of t. This is called the time constant. This is the time constant. The circuit. Okay, and this is the general solution of a first order ODE. Right? Typically, to solve this, we can solve for those constants for any general case by understanding, for example, how do we solve for K1? Because we solve for K1 from understanding the steady state condition. If we know what the circuit reaches at the end, at steady state after the transient ends, and typically we can easily do that, because notice here we have e minus t over tau. If t approaches infinity, e minus t over tau approaches 0. So this whole thing cancels, and I just end up with K1. So K1 is going to be the steady state value of the variable, which we can calculate easily from any circuit. And then tau is going to depend on the parameters of the circuit, on the capacitors, inductors, resistors, blah, blah, blah. We'll see how it will depend on that, but it will depend on the circuit, right? K2 is going to depend on the initial condition. Not just the initial condition. It doesn't have to be the initial condition. It could be, if you know the x at any instant of time, let's say ti, where ti is an instant in time. If you know xt at any instant of time, you can calculate K2, right? Because you plug in this and you get a value for the exponential, and you end up with K1 plus K2 equals this instant that you know in time. And you already know what K1 is from the steady state, right? Equals x infinity. Because you already know what x1 is, you plug it in there and you get x2. So this is the general form of the solution, and you can easily find the constants. Tau from the circuit, K1 from the steady state conditions, and K2 from from knowing the value of the solution of the response at some instant in time, only one instant in time, right? To solve like a first order equation, you need only to know one instant in time, either an initial condition or some condition at any other point in time. It will turn out for second order systems, one is not enough. You need two instants in time, or you need to find the response and the rate of change of the response. If you remember your differential equations properly, you remember that you need two initial conditions. Okay. So the time response, the timing of the response is governed by the exponential function, right? And this exponential function behaves in this way. If t reaches tau, I end up with e minus tau over tau, e minus 1. So I end up with a scale of e minus 1. So e minus 1 is like 63.2% of initial value. So if you plot the response, you start from some value, right? V start. After tau amount of time, you reach 63.2% of Vs, and so on and so forth. So if you do the math, you'll find that 1 tau, you reach 0.3, E minus 1 is going to be 0.368 K2. 2 tau is going to be 0.135 K2, and so on and so forth. It is an exponential curve, right? So if we just plot T2 E minus T over tau, what is it at 0? It's going to be K2. Then it's going to exponentially go down, decay, and the rate it's going to decay at is 63% every tau. So this is tau, 2 tau, 3 tau, and so on. The slope, the initial slope, curiously, if you extend the initial slope of this exponential, it will intersect the time axis at tau. Right? What is the slope, by the way? The slope, what's the slope of this? The slope is the rate of change of this, right? Differentiate this with respect to t, so you end up with minus K2 over tau E minus T tau. Evaluated at t equals 0, I get up with 1. Right, so the slope is here. This is the slope, minus K2 over tau, right? And when time becomes tau times tau, we end up with the change in the y-axis of minus K2. So K2 minus K2 becomes 0. We hit the t-axis at tau if we extend the initial slope of the exponential curve. So this is the general solution, but we don't want just to solve an abstract first order differential equation. We want to try to find the first order responses for any general circuit. Right? And the way we do that is first we want to zero in on the energy storage element, either the capacitor or the inductor. Solve for its voltage for the capacitor, because that's how the energy is stored in the capacitor, or solve for the current on an inductor, because that's how the energy is stored in an inductor. Right? So that's the most general method of solving those circuits. We could really solve any variable in any such circuit. We could solve, for example, for the resistor current or the resistance voltage. The solution is going to still have the general form. But one common approach is to just look at the state variable, capacitor voltage or inductor current. Right? Why are those good to zero on? Because those are values that do not change. They are guaranteed not to change instantly with time. Why? Because, well, IC equals C dVc by dt. If Vc ever changes instantly with time, we'll have an infinite rate of change, and the current will be infinite. For I, we have VL. For inductor, we have VLL, dIL by dt. If the current of the inductor changes instantly in time, we'll have an infinite voltage. So that doesn't happen typically. Okay, so let's look at an example circuit. So let's do the example. The example is, it's the basic example with the capacitor. So we're going to do one with a capacitor, and then we'll do one with an inductor to get what the form of the time constant will be for a basic circuit with an inductor and a capacitor. It will be different. For an inductor, it will be different than that for a capacitor. Right, so I have the basic circuit for an inductor is as follows: Vs, some voltage source, and then I have some switch to introduce my transient, then I have R, and then I have the capacitor C. And we said we want to use the technique of solving for the state variable. In this case, the energy storage element is the capacitor. Therefore, the state variable is going to be the voltage across the capacitor. Right? And in this case, we want to use KCL at this node. right? So KCL implies that we need to find the sum of the currents coming outside out of the node. What are the currents coming out of the node? What is the current feeding into the capacitor? The current feeding into the capacitor is C dVt by dt, and then the current feeding into the resistor, of course, KCL at t larger than 0, after the moment the switch is turned on. Right? That's what we're solving for. So what's the current according to KCL across the resistor? It's going to be just Vt minus the voltage on the other side, which is Vs over R, equals 0. So this is the basic equation that we got from applying KCL. It gives us the differential equation. Let me put it in uniform form, the regular form. That the constant here needs to be 1. So it has then this form. It becomes dVt over dt plus Vt over Rc, I divide by C, and then the minus Vs over Rc goes to the other side. So I end up with Vs over Rc. Now we already know that the general form of the solution has to be K1 plus K2 E minus T over tau. So do we have enough information here to determine those constants, K1, K2, and tau? Yes, we do. We determine K1 from considering V at infinity at steady state. What happens at steady state? At steady state, this term goes to 0, right? E minus infinity goes to 0, so I end up with V at infinity being equal to K1. But I know what V at infinity is. At steady state, and this is like a common fact that you have to be aware of. At steady state, from the voltage current relationship characteristic of the capacitor, IC equals C dVc by dt. I mean, it's a basic property of the capacitor is that at steady state, when everything stops changing, dVc by dt stops changing, right? Becomes 0. That naturally occurs at steady state. So the capacitor has current 0 at steady state, right? So the capacitance is naturally an open circuit at steady state. What about the inductor? The inductor is naturally a short circuit at steady state. Because why? Because VL equals LdIL by dt. At steady state, the current stops changing, so this goes to 0. So we end up with Vc equals 0. Vc, a voltage, VL equals 0. A voltage across an element equal to 0 is a short circuit. Okay, so the inductor is a short circuit at steady state. The capacitor is an open circuit at steady state. Using that fact, looking at that circuit, we know that at steady state, the capacitor becomes an open circuit, and the voltage across the capacitor is just going to be the voltage Vs, because there won't be any voltage drop across the resistor. So we know what V at infinity is equal to Vs. So we established what K1 is. K1 equals Vs. That's one. We establish K2 from some initial constant, some initial. If we know V at some initial state, right, we can establish K2. So let's take T equals 0, the moment of switching. T equals 0 is the moment when we switched. Let's assume the capacitor K2. The value of K2 is going to vary depending on whether there is some initial charge of the capacitor or not. Let's assume that the initial charge on the capacitor, V0 minus, meaning the voltage just before the throwing of the switch, let's assume that's equal to 0. I mean, it's valid to assume that there was some initial charge on the cap, but let's assume it was equal to 0. So using that initial condition, at t equals 0, I get K1, which we already know, Vs plus K2, e to the power 0 is 1, so plus K2 equals what? 0. The initial condition is 0. So that tells me that K2 equals minus Vs. Okay? So we calculated K2 from knowing the value of V at an instant in time. And that instant we picked was the initial condition, T equals 0. What about tau? Well, to find tau, what we could do is we could take this general solution and plug it back into the differential equation. We know that the general solution will have this form. We'll plug it back in the differential equation. When I plug it back, I end up with dv by dt. I end up with k2 e minus t over tau minus 1 over tau. Right? This is k2. Right? I just differentiated the exponential. Right? Let me extend this. Plus Vt, which is K1 over Rc, plus K2 over Rc e minus t over tau, right, equals Vs over Rc. Okay, but we already solved for K1. K1 is Vs, so K1 is Vs. So I have Vs over Rc on this side. I can cancel. So I end up with I take this to the other side. I end up with K2 e minus t tau over Rc equals K2 e minus t over tau over tau. I end up with tau equals Rc. Okay, so just from plugging back the solution into general solution into the differential equation, I get that tau equals Rc. So I got the time constant from plugging in this the general solution back into the differential equation. I got K1 from the steady state condition, and I got K2 from the initial condition. Or I could have gotten K2 from any if I known the voltage at any instant in time. The time constant for such a circuit where you have a capacitor and a resistor and some voltage source is always going to be RC. Typically, RC circuits will always have a time constant of RC. If you wanted to check that this is true, by the way, I mean, let's say you did this calculation and you wanted to check one basic thing you can always do in engineering is you need to always check your units, right, to make sure that things are right. This would not make any sense if the units of R and the units of C don't give us time. Right? What is the units of C? Yeah, IC equals C dVc by dt. That means C equals IC. Again, I'm abusing notation, but that's fine. I'm just finding the units. IC dt over dVc. That means the units of C, the capacitance, well, I know they are farad, but I want to find them in units that I can cancel out with R, right? So the units of the capacitance are amp second over voltage, right? And the units of R, resistance, we know that resistance is voltage over current. So the units of RC is going to be the unit of R times the unit of C, amp second over voltage. Amp cancels with amp, voltage cancels with voltage. We end up with seconds. So this equation makes sense, at least from the perspective of the units or the dimensions. Right? So we said this is the solution, V of t equals, let's assume that the initial condition is not zero. If the initial condition is not zero, this would be the general solution. And we know that tau is Rc. Right? Because the initial condition is zero, if V0 equals 0, we got the solution, exact solution as being Vs plus, sorry, minus Vs. K2 turned out to be minus Vs. Right, we calculated it here. No, we calculated it here. Yeah, K2 is minus Vs. Right, E minus T over Rc. So V of T, I can take Vs out and I get this form 1 minus E minus T over Rc. This is a very common form that you will see in first order solutions. This looks something like this. Right, so this is 1, but 1 that you get, that you keep subtracting from it, something that's dwindling as time goes on. So at t equals 0, you're subtracting 1 from 1, you're subtracting 1. So you start at 0 and then you keep going up until what you subtract goes to 0 and you hit 1. Okay, so this is this sort of charging response. Okay, now I want to do like an example with a inductor. Okay, let's see. I want to see what the time, what would be. It will be the same thing. It will have the same form. K1 plus K2 E minus T over tau. The only thing is tau will be different for an LR circuit with an L and an R. Tau will be different. Right, so let's do that now. So the circuit looks something like this. We have a voltage, yeah, Vs, and then we have a switch that we throw at t equals 0, and then we have an R, and then we have an L in this case. Let's look at the circuit. The circuit in this case is going to be a voltage source Vs, a switch that we throw at time equals 0, and then an R, and then an L. The state variable we're solving for an inductor, because for an inductor the energy in the inductor is in the current. You remember the energy is half Li squared, right? So let's solve for I of t. Right, and in this case, in the case of the capacitor, we were solving for V, and the differential equation, the characteristic for the VI relationship for the capacitor was I equals C dV by dt. So to get dV by dt, we need to solve to get an equation with I, right? So we use KCL. For the inductor, VL equals L di by dt. So that to get a differential equation with di by dt, we need to have something that sums up voltages, and in this case, the only thing that does that is KVL. Right? So KVL is the technique that we use here to get the differential equation. So after t goes higher than 0, right? What happens when t goes higher than 0? The switch throws off, right? Goes off, and then we apply KVL. So let me apply KVL this way. Let me go around the loop like this. So I start with minus Vs, right? That's the voltage drop across the voltage source, and I'm just applying KVL. And then what's the voltage drop across the resistor? So this is going to be, this voltage drop across the resistor is going to be IT times R. Right, so the voltage drop is going to be, when I go this way, I hit the minus, so I have a minus. Then I move this way, I hit the plus, so I have plus IT R, right? And then plus the VL. What's VL? VL we know is L dit by dt. That's the voltage current equation of the inductor, right? Equals 0. So this would be the equation for the inductor. It will be L dit over dt plus R it equals Vs. Let me normalize it. So I end up with dit over dt plus R over L it equals Vs over L. And again, this is a first order equation. Instantly, I know that the solution will be K1 plus K2 E minus T over tau. In this case, I infinity, when t is equals infinity, this exponential term goes to 0 equals K1. And I know that I at steady state, we said the inductor at steady state is a short circuit. We said that, right? So because it's a short circuit, what would be the current at steady state? It will be Vs over R, right? So K1 is Vs over R. So we found K1 already. And the initial condition I'm going to pick here is that when the switch is off, that the circuit is open. So this is easy. The initial condition is going to be 0, has to be 0. So I0 equals 0, but I0, let me do e to the power 0 is 1. So 0 is going to be K1 plus K2. Right? I0 has to be 0, but I0 also equals K1 plus K2 because e to the power 0 is 1. So that means that K2 equals minus K1, so K2 equals minus Vs over R. Right? And now what remains is finding tau. To find tau, we said we plug in the general form back into the differential equation, and dk1 over dt is 0, and then I get K2 minus 1 over tau e minus t over tau, right? Plus R over L K1 plus R over L K2 e minus t over tau equals Vs over L, right? But then I know what K1 is. K1 is Vs over R. R cancels with R, and I end up with Vs over L, which cancels with the Vs over L on the other side. Move this to the other side, I end up with R over L K2 e minus t over tau equals K2 over tau e minus t over tau. K2 e minus t over tau cancels, and I end up with 1 over tau equals R over L, so therefore tau equals L over R. So for this simple inductive circuit, when you have an inductor with series with a resistor, you have tau being L over R. So the general solution is going to be K1, which we said is Vs over R, minus K2, which is also, plus K2, which is minus Vs over R. Let me take it out, 1 minus, and then I have the exponential remaining, which is minus T over tau. 1 over tau is R over L, right? So it's going to be R T over L. So this would be the general solution. Again, we can do the dimension checking. So I'm claiming that tau equals in this case L over R. Does that make sense? Well, we know that VL equals L di by dt. So therefore L equals VL dt over di. Therefore the units of L are voltage second over amp. What about the units of R? The units of R are volt over amp. Therefore, the units of L over R are the inverse of the units of R, which is amp over volt, times the units of L, which is volt second over amp. Amp cancels with amp, volt cancels with volt, and we get seconds. Okay, so this verifies that at least by dimensional analysis, this equation is true. I mean, dimensional analysis does not give you the right solution always. It's just a way to check that your solution is not wrong. It's not a proof that your solution is right. You might still sometimes get a wrong solution and accidentally get the right dimensions. That could happen. But it's a good way to check. Okay, So we solved basic first order circuits with the inductors, with an inductor and a capacitor, right? And that's the best we can do with a first order circuit, because if I have a circuit with two capacitors or two inductors, I end up with a second order circuit. So it's outside of the domain of a first order circuit. But we could go further. We could solve more general circuits where we have an inductor and then we have a network of resistors, let's say, right? So there are ways to think about those circuits and solve them, let's say, or we have another circuit like that, but with one capacitor. And those techniques involve doing something like Thevenin, finding the Thevenin equivalent of the circuit. So there is a general methodology that we could apply um, to solve any general first order circuit that's not just a series connection of a capacitor and a resistor, or an inductor and a resistor. So I'm going to talk about that next time, and then jump into second order circuits. Thank you, guys.